All right, in this video, I'm going to jump into series circuits. But before I do that, I need to show you, I need to go back to this slide right here and just help you to understand. We learned a lot about the battery and what goes on in there and how the battery allows this whole thing to function. We did that before. Well, now when we talk about circuits, you need to understand that circuits are really all about what goes on out here and all of the differences and nuances that can happen outside the battery. So that's what this whole section is going to be about, starting with series circuits. All right, so what is a series circuit? Well, the definition of a series circuit is that there's only one pathway for current to travel through the circuit, right? So look at this circuit up here. You can see that there's a picture of a battery. One side is negative, one side is positive. Really doesn't matter which side in this case, because as you can see, if this is negative and this is positive, there's only one single pathway for the electrons to get back around to the positive terminal, right? Which means if there is one component in the circuit that fails to operate, or if there's a break anywhere, anything like this happens, if there's a disconnection anywhere in this circuit, the whole circuit is open, the whole thing goes bad, nothing works in here. If I take scissors and cut the wire here, all these light bulbs don't work because electrons are flowing through none of them. If this light bulb burns out, the other two can be just fine, but if that one bulb burns out, the circuit is open and nothing works. Let me show you what I mean. So I've constructed a very simple series circuit, batteries connected to two light bulbs. I couldn't even use three because these light bulbs draw enough current and we don't have enough batteries. I don't have enough batteries. If I use three, you wouldn't be able to see them. And this is just a very simple switch. It's just an on-off switch. So if I push it, hopefully you can see these light bulbs are dimly lit. There is current going through them. Now, I want you to take note of that. Notice that they are not very bright, and I'll talk about that more later. But here's the point. On, off, on, off. This right here already illustrates what I've said before, which is this is a break in the pathway. This switch right now is open, and since it's open, the one pathway that I've provided, this is a series circuit, there's only one pathway for the electrons to go through here and get back around to the positive side, or the other way. That one pathway is now broken. All right. If I let's bypass the switch for now and just connect these up. So I've got the light bulbs going. If I just unscrew one of the bulbs, they both go out. This one's out too. This one's out. I'm going to do it again. Watch that one. On, off. Maybe it's better if I turn out the lights. On, off. All right, same with the other one. So here's the point. A break anywhere in the circuit causes the whole circuit to fail. I can break it here, whole circuit's broken. Disconnect it here, whole circuit's broken. Any break anywhere in the circuit causes the whole circuit to fail. This is the definition of a series circuit. So one example of a series circuit, sort of, that you've all dealt with is Christmas lights. And there's a picture here of Christmas lights. I'm sure you've seen this before, probably. You take them out of the box, you turn them on, plug them in. Oh goodness, there's one part of the strand that doesn't work. And it's just that one part. And I don't know if you've ever wondered, like, why is it just that one part? Well, the reason is because Christmas lights are actually several series circuits in parallel with each other. And here's what I mean by that. Again, when we look at our diagrams, this is a diagram for a circuit. We'll deal with these a little bit more later. But this is the basic diagram for a series circuit. And actually what's going on with series circuits is there's multiple that are connected up here. And I know it doesn't look like that. These wires, this is just a diagram. The wires are all strung through this whole thing and they move from one to the next. It's complicated. There's a lot of wire in it. But the point is, if there's anything in this particular part of the pathway that's broken, just like the series circuit that I show you, if I cut any part of this pathway, if I cut a wire, or usually the problem is with the old lights, LEDs are not as bad like this, but the old ones that were incandescent, there was just a little filament here that lit up, that when the current goes through it, it lit up. Well, if that filament goes bad, that's part of the pathway, like this one part right here, which means if that one thing goes bad, this entire pathway, this entire series circuit is bad. Nothing in there lights up. This one works, these other one work, which is the reason why the rest of the strand is okay. But then you got to go and figure out what in that one part of the strand, what bulb usually is out. And usually if you replace the bulb, you reconnect the pathway, everything works again. But sometimes the wires in these strands are so small that they can break as well. So that's a possibility. So we got to do calculations with circuits. Now these calculations are not very difficult. We're going to use Ohm's law the whole time, I equals V over R. But I want you to take some notes with this stuff because there's several things, 4 things specifically with series circuits that you need to know that are very important in order to calculate and analyze these circuits. The first thing is about total or equivalent resistance. Now, we should probably first talk about what that is. So the idea of equivalent resistance is this. So all circuits have equivalent resistance, and this is not just a series circuit thing, it's also parallel circuits. What equivalent resistance is that if I take all the resistors in a circuit, say this one, I can replace all of the resistors with just one resistance that does the same job. In other words, I can come up with whatever the total resistance of these 3 resistors is and replace those 3 with one that has that resistance, and it'll be the same thing. So that's what the idea of equivalent resistance is. And it's really important that we calculate equivalent resistance or total resistance. In series, it's super, super easy. All we have to do is add up the individual resistances. So if you look at this diagram I have here, imagine the switch is closed. First of all, we're going to label our resistors, R1, R2, and R3. Actually, this is probably backwards. It should be from the negative to the positive where the current goes to first, 1, 2, and 3, but it really doesn't matter. It really, really doesn't. We're simply going to add them up. So in your equation chart, when I put the equations in the quizzes, it's going to look like this. RT equals R1 plus R2 plus R3. And the dot, dot, dot means however many resistors there could be 4, 5, 6, 27. It doesn't matter. You add up all of the resistances. So for instance, in this particular circuit, if R1 is 10, R2 is 20, and R3 is 10, 10 plus 20 plus 10 is 40. The total resistance of this circuit, or the equivalent resistance, is 40 ohms. Now I want you to notice that that's a pretty high resistance. And keep in mind that in the series circuit I just showed you, I couldn't even put 3 light bulbs on here because the resistance would have been too much and there was no current flowing through them. So that's how to calculate total resistance in a series circuit. Next, number 2 is about current, right? So we know current is running through the circuit. Remember, the variable for current is I, resistance is R. Current is the same through the entire circuit. You need to write that down. You need to remember that. Now, this doesn't mean that the current cannot change, right? I can change the current, and I did that in the circuit earlier by changing the number of light bulbs, right? So I'm back to my series circuit again. I've got these 2. If I change the number of light bulbs, I can change the current, right? So if I bypass this one, plug it in the other side to where, oh, there's something weird in that. Oh, that's the spring. Bypass this one, turn it back on. Now just this one lights up because this one is being bypassed. Notice it's much brighter. It's much brighter. And the reason it's brighter is because I can change the current. Dimmer, I've increased the resistance, which drops the current, which makes them less bright. I can change the current. So it's important that we remember that. Because it's a common misconception. People think, oh, current is the same throughout the entire circuit. That means you can't change the current. No, that's not true. I can change it. But whatever that current is, it's going to be the same everywhere. Each individual resistance doesn't matter. They all have the same current. This one is 10 ohms, 20 ohms, 10 ohms. It doesn't matter. They all have the same current flowing through them, even though they have the same resistance. Current is the same all throughout the whole circuit. In each wire, each part of the wire, in the battery, everywhere it's the same. And current is calculated by, as I said before, by applying Ohm's law, which is I equals V over R. And we're going to use the equivalent resistance, which we just did in the previous slide. It was 40 ohms, remember? We did the equivalent resistance here. And if we assume that, let's say this battery is 10 volts, right? So I can calculate the current using the voltage of the battery, plugging that into V, which is 10, using the total resistance, which is 40, plugging that into R. I equals V over R, which is 10 divided by 40. My current is 0.25 amps, and it's 0.25 amps everywhere in the circuit. Right here in this wire, right here in this wire, in R3, R2, R1. The current is the same. Doesn't matter what's going on. It's kind of like if you think about one-lane traffic. Like if there's a wreck on the highway and we've closed down all the lanes except for one. If that's the case, everybody's going the same speed through that spot, regardless of how fast their car is. You could have a Lamborghini and a the Geo Metro, and they're going to be going the same speed. And the reason they're going the same speed is because there's only one pathway. That's the key to this series circuit thing, is that there's only one pathway. It's really important that we understand that. Next thing we want to talk about, number 3, is voltage drop. So let's talk about what that means first. There is a decrease in electrical potential, which is kind of like energy. There's a decrease in energy as voltage or current flows across a device. So as it goes across R3, as it goes across R2, as it goes across R1, realize that there's some work being done in that resistance. There's some energy being lost. So that means there's less voltage available. There's a voltage drop across each one. There's less voltage available to the next one. Because the current has to go through R3 before R2. If this battery was switched up, it would be R1, then R2, then R3. There's a sequence, a series. So in series, the voltage drop across any resistor or any device is again calculated by using Ohm's law. Notice this is going to come up a lot. For that specific resistance, right? So if we solve for voltage using Ohm's law, we get V equals I over R. V is our voltage drop. V is voltage. So if we just look at R1, right? R1 is right here. We know that we want to get the voltage drop across R1. Now, it's really important that we don't plug in 10 right here, because it's not how much voltage is available to R1, it's how much voltage is lost across R1. So the voltage drop equals current times resistance. Well, we just calculated the current in the previous one. We know that it's 0.25 everywhere, and we know that this one's resistance is 10. 0.25 times 10 is 2.5. 2.5 volts drop across R1. R2, same thing. We know the current is the same, but the resistance is different. 0.25 times 20 is 5. We get a 5 volt drop across R2. There's much more of a voltage drop. And then R3 is back to the 10. It's the same, 2.5. Now, one other note about voltage drop, you might have noticed this. The total voltage drop, adding up all these numbers, if we add up all of those voltage drops, total voltage drop in the current in the circuit equals the voltage of the battery. So notice 2.5 plus 2.5 is 5, 5 plus 5 is 10, 10 is the voltage of the battery. That's going to be one of our checks when we do this later on. So these are some really important things to remember when we analyze series circuits. Now, I know right now this doesn't make a lot of sense to you, but as I start the next video, I'm going to give you a way to do this that's going to make total sense. So just hang on.